What if you were frozen alive, like in the movies where people wake up 100 years later? Could science ever make that possible? This isn't science fiction. Cryonics researchers are actually trying to freeze and revive humans, but the science is brutal. When your body temperature drops below 0°, your cells begin to crystallize. Water inside them freezes and expands, tearing cell walls apart. That's why frostbite kills. Your tissues literally shatter at the microscopic level. Imagine a world where death isn't the end, but merely a pause, a state of suspended animation from which you could one day return, healed and whole, to a future you can only dream of. This isn't a scene from a science fiction movie, it's the audacious promise of cryonics, a procedure that pushes the boundaries of life, death, and what it means to be human. At specialized facilities like Alcor in the United States, this promise is pursued with clinical precision. The process begins the moment a patient is declared legally dead. A rapid response team stabilizes the body using life support equipment to maintain blood circulation and prevent brain deterioration. The body is cooled, and the patient's blood is replaced with organ-preserving chemicals. But this is where cryonics diverges from simple freezing. If you were to just freeze a body, the water inside its trillions of cells would form sharp ice crystals, shredding cellular structures and making revival utterly impossible. To prevent this, cryonicists use a process called vitrification. They perfuse the body with high concentrations of cryoprotectant agents, a medical-grade antifreeze. As the temperature drops, these chemicals prevent ice from forming. Instead, the body's tissues enter a stable glass-like state, preserving their structure down to the molecular level. Finally, the patient is placed into a large insulated container called a dewar and slowly cooled over several days to the stable temperature of liquid nitrogen, a chilling 196 degrees C. At this temperature, all metabolic processes cease. The patient is in a state of biological stasis. Waiting. But waiting for what? The ultimate goal is to preserve the one thing that makes you, your brain. The underlying belief is that our memories, personality, and consciousness are encoded in the physical structure of our brain's neural connections, the connectome. If that structure is preserved, the theory goes, then the information that constitutes your identity is also preserved. Cryonicists are betting that future technologies, perhaps centuries from now, will be able to reverse the process. They envision fleets of molecular nanobots swarming through the body, repairing cellular damage from the original disease, the aging process, and any imperfections in the cryopreservation itself. Once the body is fully repaired, it could in theory be rewarmed and revived. It's a breathtaking vision, but it's crucial to ground ourselves in the present reality. And the reality is, this has never been done. No mammal, let alone a human, has ever been revived from a cryopreserved, vitrified state. The challenges are monumental. The cryoprotectant chemicals are toxic. The extreme cold can cause thermal stress and fracturing. And we still don't fully understand the complexities of the human brain or consciousness. Is identity truly just the structure of the connectome? Can it be rebooted like a computer? Critics argue that cryonics sells false hope, as the damage incurred is simply too great to ever be repaired. So, cryonics remains a grand experiment, an ambulance to the future with no guarantee of arrival. It's a declaration of faith in the progress of science, and a rejection of the finality of death. For those who sign up, like the first ever patient James Bedford back in 1967, it's the ultimate gamble, a choice between certain oblivion and a slim, frozen chance at a second life. However, nature can. While we grapple with the immense technological hurdles of preserving human life in the cold, the natural world has already produced masters of cryopreservation. Across the globe, countless species have evolved incredible strategies to endure lethal freezing temperatures. They don't just survive the cold, they embrace it, turning a deadly threat into a temporary pause. For these creatures, winter isn't an end, but a state of suspended animation, a quiet waiting for the return of the sun. Perhaps the most astonishing example is the humble wood frog, found in the forests of North America. As autumn gives way to the biting cold of winter, this small amphibian doesn't burrow deep underground to escape the frost. Instead, it finds a shallow hiding spot under some leaves and prepares to freeze solid. When the first ice crystals touch its skin, it triggers a remarkable internal cascade. The frog's liver begins working at a frantic pace, converting vast stores of glycogen into glucose, simple sugar. This glucose is pumped into every cell in its body, acting as a natural antifreeze, or cryoprotectant. Within hours, up to 70% of the water in the frog's body turns to solid ice. Its heart stops beating, its lungs cease to draw breath, all brain activity flatlines. By any clinical definition, the frog is dead. But here's the crucial trick. The glucose-saturated solution inside its cells prevents the formation of sharp, destructive ice crystals that would otherwise shred the delicate cellular machinery. Ice is allowed to form, but only in the spaces the cells, encasing them in a protective, frozen matrix. The vital organs are essentially shrink-wrapped, shielded from the physical damage of freezing. For the entire winter, the wood frog exists in this state of frozen stillness, a tiny, icy statue that is biologically inert, waiting patiently for the world to warm up again. It's a strategy of profound risk, but one that nature has perfected over millions of years of evolution. Then, as spring arrives and the ground begins to thaw, the magic happens. The ice melts, and within about an hour, the frog's heart flickers back to life. It begins to beat, slowly at first, then with increasing strength, pumping the glucose-rich blood through its veins, reawakening every organ, system. Breathing resumes. The brain powers back on, and before long, the wood frog simply hops away, ready to find a mate and continue its life cycle as if it hadn't just spent months as a solid block of ice. This incredible feat of survival is not just a biological curiosity, it's a roadmap for medical science. Scientists study them to understand cryoprotection, the biological antifreeze that prevents cell damage. The key is that the frog's method is incredibly effective and completely non-toxic. The cryoprotectants currently used for preserving human cells and tissues can be harsh and damaging. If we could replicate the wood frog's glucose-based system, the implications would be revolutionary. Imagine being able to freeze a donor organ, a heart, a liver, a kidney, for months instead of mere hours. This could transform organ transplantation, eliminating waiting lists, and saving countless lives. It could change how we store blood, preserve engineered tissues, and perhaps one day, provide the crucial missing piece to the puzzle of making safe human cryopreservation a reality. Could we one day freeze humans safely? Maybe, if we can learn to replace our water with cryoprotectants like glycerol or antifreeze proteins. We're closer than you think. So, let's be clear. If you were cryopreserved with today's technology, the journey would end before it began. The water in your 70 trillion cells would freeze, forming microscopic, razor-sharp daggers of ice. These crystals would shred delicate cell membranes and shatter the intricate, irreplaceable web of neural connections that holds your memories, your personality, your very self. In short, you would die. But as we've seen, the story doesn't end there. The key isn't freezing, it's vitrification. By replacing the water in your body with cryoprotectant chemicals, scientists can cool you to the temperature of liquid nitrogen without a single ice crystal forming. Your body would enter a state of suspended animation, a stable, glass-like solid, where all metabolic processes cease. It's no longer science fiction, it's a science in its infancy. However, preservation is only half the battle. The true challenge, and the great hope of cryonics, lies in the revival. This is where the future of medicine becomes truly awe-inspiring. Imagine a century from now the rewarming process begins. An unimaginably advanced medical team is deployed, not of humans in scrubs, but of trillions of microscopic nanobots. These molecular machines, programmed with the complete map of a healthy human body, would swarm through every tissue, every cell. They would be the ultimate repair crew, patching torn membranes, rebuilding damaged proteins, and, most critically, restoring your mind one connection at a time. They could even be tasked with curing the very disease that led to your preservation in the first place. Of course, waking up would present a new set of profound challenges. Would you still be you after such a fundamental, technologically assisted reconstruction? How would you cope in a world where everyone you've ever known is a distant memory, a footnote in a history book? These are the monumental ethical and philosophical questions that future generations will have to answer. The revival of a person would not just be a medical procedure, it would be a societal event, forcing us to redefine what it means to be human. But if these hurdles can be overcome, what a world you might wake up to. A future free from disease, aging, and perhaps even scarcity. A civilization that may have reached for the stars. In the end, cryonics isn't just a medical procedure, it's a wager. It's a bet against the finality of death, placed on the relentless, exponential curve of human ingenuity. It's a leap of faith, a message in a bottle cast into the frozen ocean of time. Imagine if time travel wasn't a journey through space, but a journey through ice.